Recording. Okay, so in yesterday's lecture, we saw a really nice example of where we changed the usual assumption from our no claims discount model, which was a little bit twist added, and that entailed the usual Markov, the usual chain that we have, to not be a Markov chain. So we saw that the very fact that we can come to this 25% from either 0% or from 40% impacted the future probability of going into 60% or 40%. So what we did was we realized that the solution, a sleeky solution, would just be, to split this particular state, which is creating the problem, into two parts. So we said the 25% minus represents the state wherein there was no claim in the previous state, and where I have 25% plus, it means that there was a claim in the previous state. So I know that if I am at 25% plus, I know that I have come from 40%. There is no way I can come to 25% plus from 10%. So I know that the probability that if there is the chance that there will be no claim in future and will still be 3 by 4. So you'll just move forward to 40% and you'll move from 25% minus to directly 60%, because you would know that by the very nature that you are in this particular state is because there was no claim in the previous state as well. So now if at all, again, you do not incur a claim, you are not going to move only one step, but two step forward in the discount level. And then we just had a look at, other kind of models, and one of them was random walk model. And we saw that, we can kind of generalize its formula using what we have studied. And we also tried to, be careful about when these probabilities exist. So we tried to see what are the usual restrictions that should always be true. And we got one particular condition, and the other one was that this should be an even number for it to be divisible by 2. So that was it. And then we also had to look at, 3 different kinds of boundaries that we can have. Reflecting will be the one where, you reflect out. So let's say if you are at state 4, there's no way that you will be at state 4 again. You will always reflect back to 3. So then again, if it's absorbing, then there's no way you will go anywhere else. You will just stay in the state which is absorbing state. And again, whenever I'm talking about boundaries, I mean these and this. So because this and this denotes my boundary. This is like, let's say we can call this a lower boundary and this is the upper boundary. So what's going to happen here and what's going to happen here. So what I have done is I have just trimmed my random walk model and kept P1 minus P as same, but instead just changed this boundary probabilities. And now depending on what the value for my alpha is, I can categorize it as either of these 3 boundaries. So I guess that was pretty clear. And then we also, we saw some examples. And then we also saw some terminologies wherein, then we also studied the accident proneness model, right? Which was about the number of accidents. And we saw that Y is not actually Markov, but are X, and which is the cumulative number of accidents that you have. That is indeed a Markov chain. So, that does follow a Markov property. So you can represent that as a Markov chain. So I guess that was good to know. But again, then we studied something about irreducibility. So what it simply says is that you should be able to go from any state to any other state. So that's it. And again, when I'm saying that you have Pij and N, again, it doesn't matter how much time step you'll have to take. But what matters is that you should be able to go. So this is true for any ing. Okay, and then we saw that, let's say if we have a chain like this, I know that, just to write its transition matrix, it would be something like this, right? And now if you see, there's no way you can go to 2 from 1. So it's not irreducible. Whereas this, seems like it is irreducible because there's always a chance that you can still go to 2 if you're at 1 and otherwise. So I did. Oh yeah, there was. Okay, I thought this was all gone. Okay, so then we also studied about periodicity and what does it mean by period. I gave you guys 2 different examples. So it's basically in nutshell, it's saying that, let's say if you're starting at 1, how much of a round, how much of a step you will have to take to again come back to 1. And the greatest common factor of all of those number of states will be your period. So that was it. And then we also saw that if at all there is a self-referencing loop for any one of the states in the chain, then you can easily see that, that is going to be, that particular state is going to be aperiodic. And because if it is irreducible, you can also see that you can reach any other state from any state. And even if one of the states is self-referencing and the chain is irreducible, then you would know that all of these states will have the same periodicity. So 1 we know for sure has a period of 1, and that is why 2 and 3 will also have a period of 1. And when this is the case, what I mean by this case is whenever all these states in a particular chain have a period of 1, we call that chain as a periodic chain. And again, that is why, because let's say if there is a period which is greater than 1, then that would be a periodic chain, a periodic state. And for all of those, if you have greater than 1, then of course that would be a periodic state. Otherwise, it's going to be a periodic state. And now we'll see that, so again, tell me one thing, guys. Now you have, I guess, not exactly, but a fair idea of what stationarity means. So whenever I'm talking about stationarity, it kind of means that, the process, the process does not stay where it is, but it kind of, the probability that you will stay, the probability that you will come to a particular state remains the same, right? Irrespective of how much further in time you are looking at. So if you have a periodic state, you know that it will keep oscillating forever, right? There's no way you will be at 1, you'll be at 2, or you'll be at 3 forever. So you know that this will always keep oscillating. Whereas let us say if you have something like aperiodic, you see that there is some positive chance that you will stay at 1 again. So we'll see that, it is fairly easier to figure out stationarity in the case when you're looking at aperiodic cases. And let me just explain you guys what stationarity means first. And we were discussing this example of a coin toss. So what I was saying is, let us say we have 2 states, heads and tails, as usual in a coin toss. And this is the usual probabilities that we have, right? So if I have observed a head today, there is a 0.5 chance that I will observe a head tomorrow, and a 0.5 chance that I will observe the tail tomorrow. And so will be the case for the tails as well. So just to give you guys another way to interpret this particular transition matrix, what you can also say is that if I roll a dice 10 times and I observe a head, so okay, today I have observed a head, okay? And now if I roll a dice 10 times, 50% of the times, that is, I expect 5 times out of those 10 times to see a head, and the rest of the 5 times I expect there to be a tails, right? So this is kind of saying you the number of heads you can have and the number of tails you can have. Does this make some sense? And again, if you just have a look at this same transition matrix in terms of 0.5, and if you see it as, the proportion of the total time. So let us say when you're moving forward 1 time step, the total number of time you are leaning forward is 1. So you are saying that 0.5 proportion of the time, that is 50% of the time, you expect to spend your time in the heads state, and 50% of the time you expect to spend your time in the tails state. And that is what is another way to interpret this transition diagram, this transition matrix. So again, let me just say that, this is the transition matrix. So let's say this is my P, and let's say start it off with something. So let's say I have observed the heads today. So I'll start with something like this, 1, 0. And then if I want to move forward in time, I will again have, this transition matrix here, which will get multiplied and you'll get some answer. So again, this is a 1 by 2 vector and this is a 2 by 2 matrix. So you expect a 1 by 2 vector here. So you can just write something like this, and what you will have is 0.5, 0.5, right? So this will be your distribution of heads. So whenever I'm saying that this is the distribution of heads, what does it mean? That, my heads can either take a value of heads or a value of tails in the next time step. So I'm saying that 0.5 is the probability that it will take heads and 0.5 is the probability that it will take tails. So when I say it will take tails, it kind of is not that intuitive, but just to say that, 0.5 times you will expect to land heads and 0.5 times you will expect to land tails on the coin that you have tossed. So yeah, that is what's happening here. And remember, this is only for the heads. So what I have assumed is that I have observed a head today. So this is the chance that I will observe heads and tails tomorrow. So this is not one single probability, right? We do not know for sure which one of these is going to happen. But we certainly can say that, this is the probability that you will observe heads and this is the probability that you will observe a tail. So that is it. And now let us say that I want to see what happens 2 time step later. So what I will again have is 0.5, 0.5 multiplied by P again, right? And you will observe, so this is half, half, right? Half times half plus half times half, which will be 1/4 plus 1/4, which will be what, 2/4, which will be what again, 1/2. And the same will be the case here as well. So you see, you started off with half and you again end up with half. So that's something cool. But let us see what happens next. So if I want to, let's say, move 3 time steps ahead, I see that I'm again starting off with the same thing, right? And again, I'm multiplying it with the P. So once I get something where this vector is indeed equal to this vector, and I have a P here, then I know that for every next time period that I see in future, my probabilities is going to be the same, right? So the probability distribution for the heads is going to be the same, right? Does this make some sense to you guys? So basically, what you're expecting is that if you start with a head, half of the times you expect to land up with heads and half of the time you expect to land up with tails. And again, this is just, another way of letting you guys know that this chain is forever going to be in this state. So again, if you start with 0 and 1 here, you will still get the same answer. So you remember when Hethavi showed you guys stationary distribution, I actually wasn't able to attend the whole of her lecture, but the probability in the row 1, in the row 2 was the same, right? So what does it mean? Now forget about this example. Let us say if we move back to our MCD model, and if you have a look here at its transition matrix, okay, let us check this model, right? So what we are saying is, it doesn't matter what you observed in the previous state. It doesn't matter where you are today. The probability that you will be in future at 0 state is going to be the same. So you will observe the same probabilities here. Row 1, row 2, row 3, row 4, row 5 will all have the same numbers. And what's going to happen is that it doesn't matter if you are starting at 3 or 2 or 1 minus or 1 plus. You will have the same chance of landing in these respective states. So let's have a look at that formally, I would say. And let me just write the heading that now we are trying to analyze the long run behavior. So again, what I'm going to do now is, let me define this particular vector by pi. So I just use a vector pi, and I say that this vector pi, if I multiply it by p, this gives me pi back, right? So I know that whenever this sort of a thing happens, I know that this pi is my stationary distribution. And when I say that this is my stationary distribution, what I actually mean is that this is the proportion of time that I expect to be in each of these particular steps over a long term. And again, in the heads and tail case, you don't even have to wait for the long term, right? It is there from the start. So the chain, the Markov chain is already stationary. But again, to figure out sometimes the stationary distribution, you have to think beyond. And again, why do we even care about stationary distribution? It is not that, it's really easy to calculate. I'll show you guys how we figure that out. But again, what helps us, if we know that this particular chain has a stationary point and this can achieve stationarity, we can easily say that, if my m is very large, I can just figure out its stationary distribution. And I know that that will be indeed the probability that I will observe myself in the state 0 or 1 or 2. So let us have a look at formally, how do we even say? So again, let me just write that this will be something like a 1 by m vector, let's say, and this will be m by n, m by m, and this will be again 1 by m, where your m is the number of states you have. So again, we are looking at discrete states, and that is why you can write the number of states you can have. If you were looking at continuous states, then you can't possibly measure the states that you are in, right? And again, you can't possibly be in one particular state. You'll have to look at intervals. And the possibility that you will be in one state will be 0 always. So I guess that was it about this. But again, this is one thing. So what I'm going to do now is, I can define my pi again as well, right? So what I can rewrite here, let us say I want to write the corresponding probabilities here. So what is this? This will be my P, where I started off with heads and I land at heads again, right? And this will be my P, where I started off with heads and I land at tails. So this was P11 and P12, right? So in similar way, what I'm going to do now is I can define my pi here. So I can say that, my pi vector is nothing but something like pi 1, pi 2, up until pi m. So again, why have I not written this one here? Because it doesn't matter, right? Whether you start with heads or with tails, you know that this probability is going to be the same. So what you care about is, where do you land in? So the columns, so these numbers are derived from the columns. Let me see. Here, these are derived from the columns. As it doesn't matter where you are today, right? So whenever I'm looking at stationarity, I know that it's going to be same throughout, irrespective of whatever state I have started in. Okay, so that's good. And now again, you can just rewrite this thing in terms of what's given in your books. So what they have given you is the probability that you will observe this one particular pi 1. So what I'm defining is Now I say that what will be my pi j? My pi j is now just a number, right? It is a 1 by 1 number that I have. So what will it be? Again, I'm going to use my Chapman-Kolmogorov, and what I'm going to say is that this pi j, which is the probability that you find yourself in the state j at a particular time, is just going to be the total probability of the last transition that took you into the state j, right? And then you always basically, so what I can easily rewrite here is that pi I. So this is the times that you were in state I, and then this is basically the proportion of time that you spent in state I, and then you multiply it with the probability that you jump from I to j. Okay, and again this I can be arbitrary, like the case that we studied earlier. So this I here is what you'll be summing up across, and again this I belongs to S, and this S represents states here. So again I can say that my J goes from 1 to M, right? And whenever I'm looking at one particular probability, so this is the probability of the probability that you find yourself in a state J in some particular time moment, and that is just equal to the total probability of the last transition that will take you into the J. And again, I know that this can happen in various ways, so that is why you just sum it up across to get the total probability of getting into J. All right. And again, you can just summarize this by I times Pij as also, the frequency with which transitions of I to J will occur. So again, whenever I'm saying frequency, in simple words, it just means that, I'm considering all the transitions that will lead me to J. So it doesn't matter where you come from, and you just want to take into account all the probabilities. So this was it about the way we write stationarity condition. So you'll get certain equations by using this, and those will be known as balance equations. So let me just not write that term for now, but we'll see what happens. So you see, the very nature that you start off and you multiply it with P and you stay in the CM gives some credence to the fact that we are calling this a stationary distribution. So I guess this is really cool. And again, what matters the next, so this is 1. 2, I know that all of these pi j's, because this is some proportion, this should ideally be greater than or equal to 0. And I know that all of these pi i's should sum up to 1. So that will be my third property, which we generally call normalization, because it adds up to 1, and that will allow you to basically solve your equations. So again, my J belongs to in state space, and my S is basically from 1 to M. So I know that, these are the 3 conditions that I need to be satisfied to figure out and essentially say that this pi j here is the stationary distribution. So this pi j here is the stationary distribution. So to be precise, this will be stationary probability distribution. Again, I would say, let us just try to solve a question, and then I think that will be much more clear. What exactly does it mean when I'm talking about the stationary distribution? So again, remember, not always for all the Markov chains that you will have a look at, not always you will find that there will be a stationary distribution. At times, there can be no stationary distribution. At times, there can be a unique stationary distribution. And at times, you can find multiple stationary distributions. So again, that depends on the kind of a chain that you're looking at. And we'll have a look at such examples again. So remember, I guess this is all you need to know about the stationary probability distribution for now. So there is so much of intuition that goes behind this. But again, one thing that you have to remember is that I do not know which state I'm going to start in, and I do not know in particular which state I'm going to end in. All I can know is the distribution of the states from where I'm starting and the distribution of the states where I'm going to end up in. So that is why you figure out these distributions, and that is why instead of figuring out, just stationary something, you figure out a stationary probability distribution. So let us try to have a look at the NCD model that we saw. It's the simple one, I would say. And if you remember the transition matrix, let me just go back, I guess. Oh, yeah. So I guess we're talking about this. Do we have 3 states? No. Let me check. Okay. Okay. So what I'm going to do is I'm going to stick to. So let us think about this model, I would say. Let us write the whole transition matrix for this model, and then we'll just copy and paste it over there. Okay, so let me do that, I guess. I really cannot escape writing the transition matrix. All right, so let us write the whole transition matrix. The states are 0, 1 minus, 1 plus, 2, 3. Okay, so for now, just forgive me. What I'm going to do is, okay, yeah, let's just keep it at that, I guess. 0, 1 minus, 1 plus, 2 and 3. So from 0 to 0, 1 by 4, 0 to 25 minus, 25 minus is 1 minus, 3 by 4, 0 elsewhere, 1 minus to 0 is 1 by 4, and 3 by 4 to 60. Just let me know, okay, if I commit any mistake. So then we have 1 plus, and 1 plus to 0 is 1 by 4, and to 40 is 3 by 4. And from 2 you can go to 60, which is 3 by 4, and to 1 plus with 1 by 4 chance. If you're at 3, you can 0, 0, 0, 1 by 4, 3 by 4. Okay, so now I'm just going, this is my nightmare. Okay, fine, we just keep this. Okay, so now what I want to do is I want to figure out the stationary distribution for this NCD model. So what I'm going to do is, let's just start off with figuring out the steady state probability that I will find myself in state 0. So again, whenever I'm saying that I want to figure out the steady state probability that I will find myself in 0, it doesn't really matter if I'm looking at this or this, right? Because I know that this and this are going to be equal. So what I'm going to do now is I just write pi 0, And this will be equal to what? Equal to the probability that I go from 0 to 0, which is 1 by 4, times the fact that, I was at 0 the last time. So times pi 0 plus, again, here what you have is 3 by 4. So I'm just going to write 3 by 4 times pi 1. And then we have 0 elsewhere. So let us just try to, write these equations for all of these states, and that is what you'll have to do. So then you write for pi 1, and can someone tell me what will be my equation for pi 1 here?
Ma'am, here pi 1 and 1 minus state both are same.
Pi 1 and 1 minus? Oh yeah, it should be 1 minus. Sorry, yeah, 1 minus. Thank you very much. Yeah, so what will be my equation for pi 1 minus?
1 by 4 pi 0 plus 3 by 4 pi 3.
Right, plus 3 by 4 pi 3. So what I'm going to do is, I just skip this for 1 minus, 1 plus 2, and here I'm going to write 3 by 4 pi 3. This is just for, me to avoid writing all of this again. All right, so now I want to do the same for 1 plus, and it's going to be again 1 by 4 pi 0. Pi 0 is almost everywhere. And then you have plus 3 by 4 pi 2. Okay. And then again, you will write the same equation for pi 2. I mean, this is laborious, but again, this is kind of easy. So you'll have 1 by 4 pi 1 plus, and then plus 3 by 4 pi 3. Okay. And for the last step, you have nothing here. And so basically 1 by 4 pi 2 plus 3 by 4 pi 3. So now what you'll have to do is, you'll have to solve these simultaneous equations, and that's it. Because if you solve these 5 equations, so again, let's just try to solve these 5 equations, and maybe we can save the time of solving these equations. And let me just tell you a priori that what's going to happen is, one of these equations is redundant. Why? Because if you try to add up all of these 5 equations, you will end up in the RHS exactly what you see in the LHS here. So pi 0 plus pi 1 minus plus pi 1 plus, and so on, we'll see here as well. So, okay, but wait, that's not what's happening here. Okay, yeah. So what's going to happen is, if you try to solve all of these 5 equations, one of these equations will be redundant. It's not going to be of any use to figure out the answer. So that is when this normalization equation will come in handy. So what you will do is, now you will try to solve all of these 5 equations in terms of one working variable. And let's just say, I mean, you can choose whatever that working variable will be out of these 5. So now we see that, I mean, maybe it's easier to write everything in terms of pi 0. So maybe we can do that, right? Because we already know 1 minus in terms of pi 0. Okay, so yeah, I mean, I can just try to solve this simultaneous set of equations. I know it's going to be a bit tedious, but yeah, let us try to solve this. Can you guys help me with this? Which equation out of these do you guys think is the most easiest to solve?
First equation, you can have pi 1 minus in terms of pi 0.
Yeah, right. You will directly get pi 1 minus in terms of pi 0. So this equation I can rewrite as, so this I can send back here. So what I'll have is 3 by 4 pi 0 is equal to 3 by 4 pi 1 minus, right? And then 3 by 4 will just cancel each other. And I know for a fact now that my pi 0 is just equal to pi 1 minus. Okay, so now if I know that, I can again rewrite, I can again substitute this fact here and I can rewrite my pi 1 minus in terms of pi 3. So let us try to do that. So what you'll have here is pi 1 minus equal to, so again you can substitute instead of pi 0 pi 1 minus over there, and if you do that you will get 1 by 4 pi 1 minus. You'll again subtract it from there, and what you get is 3 by 4 equal to 3 by 4 pi 3. Now this is something, really, this seems really easy, I guess. So what's again happening here is that your pi 1 is again equal to just pi 3. So your pi 1 minus is also equal to pi 3. Okay, so that's good. Let us move forward. So now if you know your pi 1 minus is equal to pi 3, what you can do is you have pi 3 here, you have a pi 3 there. So you can substitute pi 1 minus over there, and you can derive an equation between pi 1 minus and pi 2. So what we want to do is we want to write the other 4 in terms of one of these. So again, now we know that all of these are just equivalent to each other. So it's making our life easier. And we need to remember that we have already used this equation. We have used this equation. So we'll try not to use all of those equations. Plus, sorry, not plus. We found that this is also equal to pi 3, right? Okay. So now if we solve this equation, and again, just tick mark because we're using this equation, what you will get is that 1 by 4 pi 3 is equal to 1 by 4 pi 2, right? So this is again going to be just equal to pi 2 as well, right? Okay, this seems like fairly easy, but it's not always going to be this easy. And trust me, I didn't actually solve this in time before, so I didn't know it was going to be this easy. But well, I guess we are in luck today. So I know that my pi 0 is equal to pi 1 minus is equal to pi 3 is equal to pi 2. Okay, so now let us try to use this equation. And what I can again say is that my pi 1 is, this is 1 plus, right? And this is pi 2. So I know that my pi 2 is also equal to pi 3. So again, what I'm going to get is that this is also equal to pi 1 plus, right? And now if you try to, now is there anything else left that you want to know? So you see that, you didn't have to use this equation. You could have not used any of these 5 equations, but here we saw that this equation is of no use to us. So we now know that all of these are equivalent to each other. And again, we also know that because this is a stationary distribution, so even forget that it's stationary, just for it to be a valid distribution, I know that all of these sums should be equivalent to 1. So what I'm going to use is, so now I use the fact, so now you'll use the fact that summation of pi j's is 1 over all the j's. So if you add all of these, you should get 1, and you know that all of these are, equivalent. So you know that all of these, the probabilities. So can someone tell me what will be the stationary distribution here for this case? Okay, so let me maybe not skip this step for now because it's maybe easier in this case. But what you will ideally do now is that because you know pi 0 plus pi 1 minus plus pi 1 plus pi 2 plus pi 3 is equal to 1, right? This is what you derive from this. So what you will do now is you will use this equality here. So you can rewrite this as, so again pi 1 minus I can write as pi 0, and I can write all of these as pi 0s, right? So what I get is 5 times pi 0 is equal to 1, which implies that my pi 0 is equals to 1 upon 5. And now that I know that my pi 0 is 1 upon 5, which is equal to all of these, I kind of know that my stationary distribution is just this. So 1 by 5, 1 by 5. Is this clear? Doubts? So again, remember what the result says is not that states are in the steady state. It just says that, so it doesn't even mean that, the process will be just where it is now. You will keep jumping around from one state to the other state. But again, what it just says is the probability that you will find yourself after a jump in this particular state is 1/5. And that is going to be constant throughout the time. So again, two things are really important here. One, the initial state does not matter. So we know that there is enough randomness here so that it doesn't really matter where do you start from. And the randomness essentially kind of, weakens out at the end. And at the end, you will always find yourself in this stationary distribution. So always the probability that you will find yourself in state 0 is going to be 1/5. And the same for all the other states as well. So again, remember, you could only define this particular 1/5 as a number once you used the fact that this summation is equal to 1. So sometimes this allows you to define this pi j's uniquely, because otherwise if you didn't know this, if you just had these 5 equations, you would have just had this equality. You wouldn't be able to say what is the value that your pi 0 takes, what is the value that your pi 1 takes. So the very fact that we know that all of these probabilities add up to 1, and again that is indeed trying to say that you have a distribution and the area under the distribution is always, and it should be equal to 1, because there is nothing else outside of the realized state spaces that you can anytime observe. So, and again, remember, it is not the convergence of process, it is the convergence of probabilities. So probabilities is what stay the same. The process again might be different. So you can actually, I'll actually show you guys, how sometimes even if the process is different, you can have the same probabilities. And that is why even if the process is not converging, the probabilities can still converge. So does this make sense?
Ma'am, so from stationary distribution, we just get the probability of being in any particular state, right?
Yeah, in the long run. Okay, so we don't expect our process to be stationary in, let's say, 1 time step or 2 time step. It will take certain time, and again we define these. So essentially, formally we say that whenever your n goes to infinity, you are certain that if there is a stationary distribution, you will find yourself in that stationary distribution. And if it, let's say, does not exist, then of course there's no way. You'll just be jumping around everywhere with no certain probabilities converging to anywhere. So sometimes if you have bigger number of steps that you are looking at, you need not have to, even multiply all of these matrices again and again and again, those n number of times. If you conclude that that particular n is big enough for this process to be stationary, for this probabilities to be stationary, then you can easily figure out its stationary distribution, and that will be your answer. So let's say if I now ask you that, let's say if you're in this particular NCD model, what is the chance that, given that I have started at state 2 today, what is the chance that I will observe myself at state 2 in 100 years down the line? So you won't have to calculate and multiply the matrix 100 times. You can just easily see, and you will kind of be expecting that the process kind of the probabilities kind of become stationary, and the answer will just be 1/5. Yes.
So for any matrix, if we increase the number of, means n goes to infinity, every matrix can be converted into stationary distribution.
Only if, there exists a stationary distribution. So not always you will have a stationary distribution. So one thing that guarantees you that there will be a stationary distribution is the fact that, let's say, if your Markov chain has finite state space. So again, in the random walk model, if you have infinite state space, you can just go anywhere, right? I mean, it's kind of not clear to see, and again you cannot easily figure out that there will be a stationary distribution or not. So we do not know what happens in infinite state space. There can exist a stationary distribution or there cannot exist a stationary distribution, but we know for sure that if a Markov chain has finite state space, so let us say, let me write it, if a Markov chain has finite state space, this implies that there will be at least one stationary probability distribution. So again, you are not guaranteed that there will be only one stationary probability distribution. At least one stationary probability distribution. Okay, and again, I mean, this proof is really not, I mean, you need to know a lot of number theory also and some measure theory to prove this, which we don't have in the syllabus. So, does this make sense? Does this answer your doubt, Mihir?
Yes, ma'am.
Okay.
Ma'am, how can we have different stationary distributions, like if we are solving the same equations?
Oh, okay. That is a good question. So I think what I can maybe, let me just fetch one example. And so it's, I mean, what will happen is, essentially what you're doing is, you're solving some set of linear equations, right? Here, you're solving some set of linear equations that you have derived from the transition matrix here, right? And whatever answers you get for these equations, so let us say that, I mean, I'm just going to give you a very, very basic example, that my x plus y, is equal to 9. So I know that my x can take 3 and my y can be 6 and my x can be 1 and my y can also be 8, right? So that is the kind of thing that will happen here. So for different values of pi 0, pi 1, pi 2, pi 3, pi 4, you can get stationary distributions. As long as they satisfy all of these conditions, all the numbers that will, I mean, the pair of numbers, the pair of these 5 numbers that will satisfy these equations and this condition, you can say that that is a stationary distribution. So sometimes you will have, more than one stationary distribution, which will just be, in the case where, let's say, I mean, you'll have multiple values which satisfy the same equation. So in that kind of scenarios, so here you had, that all of these are equivalent to each other, but sometimes when you try to solve these equations, I'll try to, point to one particular example, and I'll put it in the classroom so that it's easier for you guys to just solve it and see how you can arrive at multiple stationary distributions. And I guess it's kind of fascinating. And again, I can actually maybe just show you guys one example. So I am not going to write numbers, but let me just draw a particular chain. So that will show you how there can be two stationary distributions. So let us say there is, so let us say this is the Markov chain that I have. Okay. Yeah. So this is, let's say, the Markov chain that I have. So what's going to happen now is, let us say you arrive at this state, okay, and then you jump here. So you see that there is now no way you can escape this particular lump here. So you will always be in this particular state, right? And let's say if you are here and if you jump here, you know that there is no way out of this box. So you see that you will get one stationary distribution here and you will get another stationary distribution here. Can you see?
Yes, ma'am.
Okay, yeah, good. So I think, I can again put up some example with, numbers and all, but I guess this is the idea. So again, here it would matter where you get from, but again, once you're here, it doesn't really matter because you know that you were here and that is how you got here. So I guess that's one example of how you can have multiple multiple stationary distributions in a particular chain. Okay, so this was just, one example. And again, there is one more result. So the result that we discussed here was that if my Markov chain has a finite state space, I know that there will be at least one stationary probability distribution. But let's say if I also know that my Markov chain is not only, it does not only have finite state space, it also has, finite state space plus it is also irreducible. So if my chain is irreducible plus it has finite state space, then I will have for sure a unique stationary probability distribution. So this is another result. I will just maybe write here important results. Yeah, so this is 1, this is 2, and we'll come up with the third one now. So you see, again, what do I mean by reducibility? I can move from any state I to any state j. And the probability is always, greater than 0, irrespective of how much ever time it takes for me to reach that state. But I know there is some possibility that I will reach that state from the other state. So if that's the case, and if you have finite state space, then you're guaranteed a unique stationary probability distribution. And again, this proof is beyond the syllabus, so I guess it's fine. But again, I think let us just do one more set of example and let's see. So, okay, maybe we can try, let's just try this, or maybe I can give you guys this as homework. So what you will have to do is, this is a chain, okay, 1 and 2, self. So this is 1, this is 1. So I think I wrote this at the start of the lecture. So give me a stationary distribution for this process. So just consider this as your homework and try to do this for fun. So you can see clearly that, this process is not irreducible and this has finite state space. So just tell me what will happen here, and yeah, forget about it for now. That's your homework. So now what we are going to do is, we are going to have a look at another process, and now I want you all to, maybe I can, so is it okay if I skip the solving part in the lecture? Maybe I can just allow you guys to go through that. Let me open the book, I guess. Yeah. So let us say this is the Markov chain that I'm looking at now. Then what's going to happen with this? So here you can see that, this is, okay, yeah, this is the kind of chain. So if you were to draw a diagram for this particular transition matrix, you can see that from 1 to 2, so the probability that it will go is a half. From 1 to 1 is a half. And you'll come back is a half. And you'll stay there is a half. Right? Okay, and if you are in 3, you're just going to be there.
And 2 to 1, the probability is 1 by 3.
Okay, sorry, 2 to 1 is 1 by 3, and here then it will be 2 by 3. Yeah, thank you very much. But yeah, you see the arrows? That is what matters here, right? I mean, if you are at 1 or 2, you can't possibly go anywhere else. If you are at 3, you will just stay there, and if you are at 4 or 5, you can have some probabilities attached. So you see that you expect that you will see multiple stationary distributions here, because again, this chain is not irreducible. But again, you cannot say that, if your chain is not irreducible, that there will be for sure multiple SPDs. What you can say is that if it is irreducible, there will be only and only one unique stationary probability distribution, again, considering the fact that you're looking at finite state space problem. So, okay, so I'm going to not indulge into solving these equations, but what you can see here is that they have tried to solve. So again, what they are going to do is they'll solve stationary distribution for this, a separate stationary distribution for this, and a separate stationary distribution for this guy, right? Because anyways, there is no possible way that you can travel from this to this or this to this or this to this or this to this back. So what we are going to do is we conclude that each of these subsets of states will have a unique stationary distribution, because you see that each of these subsets in themselves are irreducible. And again, we have finite, right? So here the number of state spaces will be 2, here it will be 1, here it will be 2, and they are irreducible, and we have finite state space. So you expect that there will be a unique stationary distribution here, here, as well as here. So now what you're going to do here is solve for each of those. So again, you just rewrite this condition where pi times p is equal to pi, and this is pi 0, pi 1, you'll end up in 0 and you'll end up in 1 state. And this is the p that you have. So remember, this p is not the whole of this, it is just this particular quadrant. So, and then you try, okay, yeah, so here you can clearly see that, if you try to, so you will be multiplying this with this, and then this with that, and you'll equate it to this and this, right? So a half of pi 0 and a half of pi 1, and 1 by 3 of pi 1 is going to be equal to pi 0, and similarly for this. So you see, if you try to rearrange these equations, they'll give you the same thing. So maybe if you see here, what you're gonna get is a half of pi 0 is equal to minus 1 by 3 pi 1, right? And the same thing you're gonna get here. So half of pi 0 is equal to 1 by 3 minus 2 by 3 minus 1 by 3 pi 1. So you see, you will have to discard one of these equations. So you say that, okay, I'm not going to take this equation into consideration, and you only work with this, and then you also check that, pi 0 plus pi 1 should also be equal to 1. I don't know, my pen is acting weird, but yeah, pi 0 plus pi 1 should also be equal to 1. And then you solve this and this simultaneously, and you arrive at some answer. So here you get pi 0 as 1 by 5, and here you get pi 1 as 3 by 5. So, and can you guys tell me what's going to happen with the third one? What will be the stationary distribution for the third one? For the state 3. So for the states 4 and 5, you are going to do the same analysis, right? The kind of, you did it for 0 and 1. But can we guess what's going to happen in 3? Because I just have, if you are at 3, you will be at 3 forever. There's no way you will escape that.
It will be 1, right, then?
Exactly right. It will just be 1, because it adds up to 1 and there's nothing else but 1. So you see that you can rewrite it as 0, 0, 1, 0, 0. So this is the stationary distribution corresponding to state 3, and this is the stationary distribution corresponding to the state, I guess, 4 and 5. Or was it for 4 and 5? Yeah, whatever, I guess. Yeah, so this was for 0 and 1, and this was for, I guess, 4 and 5. So you got 2 by 5 and 3 by 5 here, and you have 3 by 5 and 2 by 5 here. So now that you have these unique distributions for each of these separate subsets of states, you also observe that it doesn't really matter if I land up in this subset or if I land up in this subset or if I land up in this subset. I know that whichever subset I land in, that is the subset I'm going to forever stay in, right? So because all of these three subsets are independent of each other, what you think is that you can maybe represent, you can generalize thus these stationary distributions in such a manner that you just put these A, B's and C's over here. Just give me a minute. Yeah, so what I'm doing now is nothing much complicated, but rather a simple, a very simple thing. So I'm going to take arbitrary numbers, A, B and C. So these are constants. These are not variables. These will take one particular value at one particular time. Okay. So I have A, B and C, and you see I have A for the subset of 0, 1, B for the subset of 3 and C for the subset of 4 and 5. So what I did was, I know that, every time this should add up to 1. Anytime I write a particular stationary distribution, it should always add up to 1. So I see that 2 by 5 plus 3 by 5 is 1, check. 3 by 5 plus 2 by 5 is 1, check. Here 1, check, right? It adds up to 1. So again, you can do this kind of verification and remember the equations were discarded. Once you figure out these values, you can also substitute these values back in the equation that you discarded, and you should see that it satisfies that equation. If it does not, then you will clearly know that you kind of made some mistake. So I guess this is a really good thing about figuring out the stationary distribution. You can easily verify whether the answer that you have is correct or not. Okay, that's good. But again, now what I want is the general stationary distribution that I'm looking to define, even that should add up to 1. So what I do is I just have this A, B, B, C, C here. And again, if you see, in a way, I am not changing these probabilities, right? You will still have 2A upon 5A plus B plus 5C, and at one moment you can put basically different ratios over here, and what you will again here have is 3A upon the same denominator. So what matters is the ratio, right? How much time do you expect to spend in a particular state? So here you expected to spend 40% of your time in state 0, and here you expected to spend the rest of the time, which is 60%, in your state 1. And that is the same you're going to observe here as well. So what we have done is, instead of writing these three separately, we have just generalized it. And again, if you see the ratio, this remains the same because it will still be 2 to 3. This will still be 1. And this will still be 3 to 2. So that is what you will always have. And now if you add up all of these, you know that this will again sum up to 1. So this is how you can generalize the stationary distribution. And now you can clearly see, depending on the values that I assign to A, B, and C, I can get multiple stationary distributions. So now they have assigned 1, 2, and 3, and you have this as your stationary distribution. And if you assign other numbers, you will get different stationary distributions. So here, I guess this kind of solves your query with a numerical example as well of how you can have multiple SPDs. Any doubts in this? So again, here what was happening is you got trapped, once you enter, the place where you start is where you will end up, the subset. Okay, yeah, any doubts? Again, what matters the most is that your end ratio remains the same. And you could do this only because these were independent and you just created a linear combination of these. Yeah. So again, if you say that, this is my stationary distribution, so what's happening here is they have, taken into account the fact that from the starting, you won't always be, you aren't sure, right, which subset you are going to start in. So again, to take that into account when you're writing a generalized stationary distribution for the chain as a whole, you have to take into consideration the probability that you will land up in one subset as well, and the probability that you will land up in second subset, and the probability that you will land up in third subset. So you culminate all of these by creating a linear combination of these, because that is how it's going to happen. And voila, you get a 1 as your addition as well. And yeah, it satisfies each of the conditions that we need a stationary distribution to satisfy. Any doubts? If you haven't understood, just ask right away. I will explain everything once again. And do let me know if you have understood so that I can proceed.
Yes, ma'am, understood.
Sorry? Okay, good. So I hope this is clear. And again, I think I'll just come back to this particular question. I find this question very interesting after a week or so and see if you still have any doubts or not. And yeah, you'll have much developed thinking by that time, I guess. Okay, so now that we know that, this process was clearly not irreducible, and we saw that we ended up with multiple SPDs, right? Okay, so again, now we also recall the fact that we studied something about periodicity. So there is one result specifically that pertains to periodicity, which will be the third result about stationary distributions here. So what I am going to say is that, let us say if I have, so I have all of these, okay. I have finite state space, I have irreducibility as well. And along with these two, if I have aperiodicity, so if my process is aperiodic, then I know that so if this is aperiodic, then I know for sure that I'll have a unique stationary distribution in the long run. So I'm again gonna write here that I'll have unique SPD in the long run. So whenever I say in the long run, it means that it's gonna be there forever, right? So to formally write this, how you will rewrite this is as something like this. So let us say I check the probability that I start in state I and I go to state J in n number of time steps, okay? And whenever I'm talking about long run, let me take that I'm going to have limits where n goes to infinity, okay? So this is always going to be equal to pi j, and this is true always, if at all a pi j exists. So again, this is only about, ending up at state j. That is why you have pi j here. And remember, I haven't written I anywhere here, right? So the answer to this particular limit is independent, again, of where you start from, because the randomness washes away. And there is no memory of where you start from in case of the stationary probability distribution. And that is what there is. So again, I guess, sometimes the process will settle down, sometimes the process may not settle down. So in this case, this process will actually settle down. So the example we saw of the coin toss, yeah, it was here, right? So if you see, the process has actually, settled down here to some equilibrium distribution. But again, I mean, in this case, it didn't really take us that long, and in general, it might take a bit longer as well. So if you check here, the probability that if you start at heads, you'll be at heads after even 2 time steps is going to be equal to a half. And again, if you also have a look at VHH at n number of time steps with limit n going to infinity, that is still going to be half, which is equal to your pi h. And the h that I have written over there comes from this h. Yeah. So the third result is all about, if you also know in addition that your process is aperiodic, you can say that it will settle down for sure with the unique SPD in the long run. But again, we can have a look at the process which is periodic and still have a stationary distribution. So it's not that if you have a look at a periodic chain, you won't see it having a stationary distribution. It might still have, but it is not guaranteed always. So you can have a look at, a simple chain which is 0 and 1, and it goes there and it comes back with probability 1 every single time. So this chain is not a periodic, right? Because there is a period of 2 every single time. Every odd times, if you, let's say, are starting at 0, you expect to come back for each even time at 0 again. So the period is 2 for each of these states, and that is why this is periodic chain. So you kind of guess that it may or may not have a stationary distribution. But here, if you try to solve, this is going to have a stationary distribution. So this is kind of, so 0, 1, 1, 0. So previously the homework that I gave was 1, 0, 0, 1. Now I have 0, 1, 1, 0. So I guess you should try this thing as well and check what you get as your, stationary distribution. And I think, if you guys were to guess what the stationary distribution will be, can you guys guess the stationary distribution without even solving for this? So another interpretation of stationary distribution is that, so let's say if I have pi 0 here and pi 1 here, I expect pi 0 proportion times to be into state 0, and I expect this much of my proportion in time to be at state 1. So from observing this particular process and without solving for a stationary distribution, can you guess what will be your pi here?
Half and half.
And why do you think so? That is the correct answer, by the way.
Ma'am, because from there is no, just a second. There are only 2 states and the probability should be 1. So it's directly half and half.
Okay, maybe try to frame it better. I think you have kind of understood, but I'll give you some time to frame it a bit better. Mihir, do you agree with half and half?
And there are only 2 possible ways. Like it can only go from 0 to 1 and again 1 from 0. So
yeah, so I guess that is the correct explanation, because there's no way you can stay at 1 if you're at 1. So you expect that at all the even times, you will be at 0, and if you start at 1, let's say, at all the, if you start at 0, at all the even times you will be at 0, and at all the odd times you will be at 1. So you see there's a 50-50% distribution around these states. So it's half and half. That is what you're going to get even if you try to solve it using, pi equal to pi p. Yeah, that is the same thing that you're going to get. So I guess that was it about stationary distributions. And that is all you guys need to know for at least this chapter. So the next thing.
In the previous example.
Yes.
You can say that it was irreducible. That is why it can have unique stationary distribution, right? From the second property.
Yes, it is irreducible and it has finite state space. Exactly. Yes. So it will have a unique state space. Yeah.
So means it is it like that for every periodic state space the distribution is irreducible?
Yeah. If you have periodic as well as irreducible, then you will observe. If you have finite state space and irreducibility, then for sure you will see a unique stationary distribution. But again, if it is only periodic and maybe not irreducible, then there's some doubt about whether it exists or not.
Okay.
Good question. All right. So now we'll have a look at how do we in actual analyze these cases. So yeah, you can also try this example. You can basically create your own chains and try the examples. Yeah, I gave you guys this example just now. And yes, it's half. Yeah, so this is the summary of the 3 results that we just saw. But this is also interesting, I guess. So what we're going to do now is have a look at how do we actually model Markov chains. So I know that sometimes I do not know if a chain exists or not. All I can see is a process. So this is a process that I have observed. And again, they have given to us in the question that this is a 3-state process. So my state can either be 1 or 2 or 3. Cool. But I don't know my transition metrics. I don't know any probabilities. So what do you guys think I can do now? Let us say this is what I have observed and I want to figure out my transition metrics. Let's say Pij. So 1, 2, 3, 1, 2, 3. How do you guys think I can figure out this probability that I can go from 1 to 1? What is the first thing that comes to your mind when you see this?
Ma'am, is it like in the given process 1, 3, 2, 1 is repeated after 1 only once?
Yeah, that is half of it. So yes, 1 is repeated after 1 only once, correct? But that will be my numerator, right? So whenever I'm talking about a probability, it should be one particular
sample space, total number of ones.
Yeah. So will it be total number of ones? What do you think? Will it be total number of ones? Or will it be something else? Sauri, what do you think? What are we looking at? Are we looking at the times we are in state 1? No, right? We are looking at the times we go out of state 1, right? So we'll have to look at for how many times we make a transition out of state 1, right? So if we have a look at that, we see that there is a 1 transition here, 2nd, 3rd, 4th, 5th, and 6th transition here. So I know that in total, the number of transitions I make out of state 1 is 6. Can you guys count the number of transitions I make out of state 2 as well as state 3? So you know that this will be something like 1 upon 6, right? Because one time you observe 1 and 6 times you transition out of state 1. So there is 1 out of 6 chance that you will go from 1 to 1 back to 1 again.
For 2 also it is 6.
Okay, it is 6. How did you count?
From 2 to 2, 1 transition. From
Yes.
2 to 1 second.
Yes.
To third transition. Again 2 to third, fourth. And 2 to first, fifth. Okay, 2 to 6, 7. There will be 7 times.
There will be 7, right? And what about 3?
5.
5? Okay, let's count again. It's not 5. 3 to 2, 1, 3 to 3, 2, 3 to 2, 3, 4, 5, 6.
6. Yeah, 6.
So it's gonna be 6. I know. So this is actually tricky and it looks very simple. But yeah, I mean 1, 2, 3, 3 numbers back to back. I know it can be tricky. But yeah, these are the total number of transitions you make out of each state, right? Total number of transitions you make out of each state. I'm not gonna write that. Okay. So now to figure out, so now what we have done is we have figured out the denominators here, right? It's gonna be 7 everywhere, it's gonna be 6 everywhere here, and it's gonna be 6 everywhere here. But now we also have to figure out these numerators, right? So let us try to figure out the numerators here. So we'll count the number of times you go from 1 to 1, number of times you go from 1 to 2, number of times you go from 1 to 3. Okay, so 1 to 1, Meir has already done that for us, it's 1. So let's count how many times you go from 1 to 2 in one time step. 1, 2. I guess it happens, it's happening 2 times, right? And we know it has to sum up to 6. So again, what you can do is you can, maybe subtract 3 if you're so sure of your counting, or else you can go back and check 1 to 3. So 1, 2, 3. Yeah, so I know 3 plus 2 plus 1, 6. Good, right? So this numerator is just going to be 2 and this is going to be 3 now. Does this make sense? Okay.
Yes, ma'am.
So now, yeah, so this is basically counting the number of transitions. Okay, from 1, 1, 1, 2, 1, 3. So again, you see this is first row, first column. So 1 to 1, first row, second column, 1 to 2. It's kind of intuitive that way as well. So now what's going to come up here? Second row, first column. So from 2 to 1. If I check 1, 2, and 3, right? It happens 3 times. And now I want 2 to 2. So this is 1 and 2. I hope I'm not missing out on things. And now I want from 2 to 3. So this is once, twice. I guess that's it. Yeah, it adds up to 7. Okay, yeah, that's a relief. Okay, now we'll check for the third row. So what do we have? From 3 to 1. Okay, it's not from 1 to 3, it's from 3 to 1. 1. I guess there's only 1. Now from 3 to 2. 1, 2, 3. I guess that's all we have. And now for 3 to 3, this is 1 and this is 2. Adds up to 6. Done. Right? So now you know the numerators as well. This is going to be 3, 2, 2. 1, 3, 2. So Mihir, if you count the number of 3's that you have here, it will add up to 7, right? But because at the end you have a 3 and you cannot make any transition Again, you are not making any transition out again. So you can, you should not resort to counting the number of numbers that you have. Maybe you can do that and then just subtract one for the last 1 year. So again, it depends on how you want to do that. So I guess that was it. And now let us have a look at, what this question is trying to ask us. This is the general idea that I guess I can give you guys. Yeah, but now we have actually figured out the transition matrix. If we feel great, we feel so proud of ourselves. We were just given this process and we figured out the transition matrix. Okay, so now what they're saying is a 3-state process has been observed, blah, blah, blah. What we have to calculate is the values of Nijk, Nij, and Ni. Okay, so I didn't explain you guys before what are these terms, but when I'm saying Ni, it means the number of I's that I can observe. And I know that my Ijk are just states here, right? So this I can either be 1 or 2 or 3. So when I'm talking about this Ni, it is nothing but this matrix right here, 6, 7, 6. So I know that my Ni can be, either N1, N2 or N3. So this is the value that you will have for Ni. So this is your Ni. Okay, and now if you are looking at Nij, this is your N. So this is your Nij here, okay? And this is basically saying transition from I to J. So the number of transitions you make from one state to the other state. That's cool. But now what about this? They're asking us about Ijk. This is weird. Whenever I define a particular element in the matrix, I can only write either a row. I can only write its row and column, right? Where does this third thing come from? So what you can do is, if you want to figure out the value of this Nijk, what you will have to do is, you are basically taking into consideration all the triplets that you can see. So something like 111, 112, 113, and all of these. So you will basically have to figure out the probability that you observe all of these. But again, the number of triplets that you will have are how many? So you have 3 states and you have 3 spaces. So this is going to be 27, right? So you know that you will have 3 different metrics. And again, this is not the reason you will have, let me just erase that. This is not the reason you will observe 3 metrics. But what you can do is, you can choose one value. Let's say I can choose, so in your books, let me just erase everything for now. And I can just go to this answer. So what they have done here is, they have chosen one value for I, which is 1 here, 2 here, and 3 here respectively. You can also choose value for J, or you can also choose value for K. But for those 2 states for which you are not choosing any value is the probability that you will have to write here in this matrix. So deliberately, I'm not going to take these into consideration, but let us try to write the Ni1K. Okay, so this is going to be a bit difficult. So, but let's try. I want to give you guys idea.
Ma'am, can you please explain once again what is Nijk?
Yeah, I'm going to explain that using this. So what I'm going to do now is, because I know I cannot write Ijk, each of these 3 in one single matrix, right? Because a matrix can only be defined, the elements in the matrix are defined only by its rows and columns. So I can only use 2 states at a time. So what I'm going to do is, to define my Nijk, I can write my Ni1K, I can write my Ni2K, and I can write my Ni3K. So these are all the 3 values that my J state space can take here, right? And I'll create another matrix for this guy, and I'll create another matrix for this guy. But now we'll see how can I create a matrix for this guy now. So I know I have 2 unknowns, I and K, and I have a row and I have a column. So this is, consistently what you do is, the first unknown that you have will be in the rows, and the another unknown that you have will be in the column. So you are going from row to column. Okay, so again here it might create confusion, because what I'm considering here is Nijk, which is like, so you go from I to J in one step and you go from J to K in another step. So you cannot possibly write 1, 2 and 3 here, because what if at all I try to write a transition matrix here, what will it denote is that I go from I to K, right, when my J is 1. So this is not kind of true, even though you can write this, but this won't make much sense, because from I to K you are taking 2 time steps. So what, I mean, if you want to write this, you can actually do that, by considering wherever you get 1 in the middle. So I know for my J, I want the value of 1 here. So I'm going to have a look at wherever I can find a set of 3 with 1 in the middle. So I'm just going to circle those. This, and then I also have this, and then another, I have this, right? So these are 1, 2, 3, 4, 5 chances that I have where I observe 1 in the middle. So what I can do now is I can look at the values of I and K that I have when I have 1 as J. So I know that this is 1, 2, 3, 1, 2, 3. But again, this is for K and this is for I, right? So here I have my I as 2 and my K as 3. Here I have my I as 3 and K as 2. So I'll check, is there any possibility where I can see my, so again, I think it's very tedious to check off for all of these 9, because we only have 5 here. What I can do is, I have 2 for I and 3 for K. So 2 for I and 3 for K. I'm just going to put a 1 there. 3 and 2. So 3 and 2. 2 and 1. 2 and 1. 1 and 2. And 2 and 3. So 2 and 3, one more. So I know that these are all the possibilities that I see. So again, remember, this is not a probability. This is not a transition matrix. This is the number of transitions you make from I to K when you have J as 1. So this will be 1, this will be 1, this will be 1, 0, 0, 0, 0, 0, and this will just be 2. So Savri, do you get a bit clearer idea of what is an IJK?
Yes, ma'am.
Mihir?
Yes, ma'am.
So you can do the similar stuff for this, and again, this is not enough, right? Because you have considered that J is 1. So you'll have to do this for 2 and 3 as well. So the values of J for 2 and 3 as well, and that will be your NIJK. NIJK, yeah. So, and so here they have taken 1, 2, 3 for I, and you can do basically it for anything else. So now what will this represent? This represents the case where J and K take the value 1, 1, right? So this is the number of transitions that you have from 1 to 1 to 1. And this is the number of transitions you have from 1 to 1 to 2. Do you get that?
Yes, ma'am.
Savri?
Yes, ma'am.
Okay, good. So that is all we wanted to know. And I think in the first question, they're asking you about this number of transitions, and then they're asking you about the one-step transition probability. So they've already seen this before. Okay, so that was good. But now, okay, so for these questions, I'll have to take you guys back to this. Okay, so I think now it's easier for you to understand this theory, and it's much easier, I guess I would say. So, okay, this is the transition probability that you have, right, within the matrix. So you see it has a numerator Nij and upon Ni. So what is Ni? The number of transitions out of state I. And what is my Nij? The number of transitions from state I to a particular state J. And because I'm looking at Pij, I have Nij in the numerator. And you do not forget the hat here, right? Because again, we are estimating based on a particular sample. So this is not a population parameter. This would be a sample parameter that you have, and you have estimated it using the sample that you have observed. So you put a hat over there. So I guess that's good. But again, if you see here, yeah, so you see it right, Ni will be equal to Nij. So the number of transitions you make from I is always equal to the total number of transitions you make from I to a particular state summed up across all the states that exist. Okay, so if you see here, they have said that, ni as the number of times t, such that xt is equal to I. So this is exactly what Mihir was trying to say, that, my ni for 1 was equal to the number of ones that I see. But again, if you see here, what they have done is, they have said that my t can only be from 1 to n minus 1. So when they are saying this n minus 1, why they are saying this n minus 1? Because again, you take into account that you lose one observation, which is the last observation, right? Because there is no transition out of that observation. So you have n minus 1 here. And similarly, whenever you are talking about an ijk, you're expecting a pair of threes. So if you have a look here, the last pair you can observe is 1, 3, 3, right? There is no pair with 3, 3 and there's nothing here. So you're losing out on 2 observations. So that is why you get n minus 2 here and n minus 1 in the previous case. Okay, so I guess now it's clear how you figure out the transition probabilities. And again, this is just for theory, but you guys know how this n minus 1 and n minus 2 come about. So now what you're going to do is, this is an estimator of Pij, right? Pij hat is an estimator of Pij. So you will also want to check how much I can rely on this estimate. So for that, you figure out a confidence interval. And if at all, let's say I'm assuming that my Nij given Ni follows binomial distribution. So I'm saying that this guy follows binomial distribution with Ni, which is the number of times I transit out of state I, and Pij, which is the number of times I go to a particular state J where I'm coming from a particular state I. So I'm looking for the probability of, Nij given Ni. So this follows binomial. And I know that to figure out a confidence interval, what I do is I take the estimator itself plus or minus the standard normal value and a square root of the standard error. So what is my standard error? My standard error is just the standard deviation upon this thing. We have taken the variance here. So actually, in actual, you can say that your standard error is actually standard deviation upon the square root of n. So if you have variance in here, what is my variance? It is just standard deviation square, right? So if you put variance upon n, you can write it, you can rewrite your standard error is as this. So here, if you see, the variance will be just p times 1 minus p here. And that is what you have here as well. So this is how, you can actually rewrite the confidence interval for the case where you approximate this with binomial. And it's not much tricky as well, I would say. So what's happening here is, now they're asking you to figure out, okay, they're talking about triplets directly. So that was it about, the confidence intervals for the estimator of Pij, which is Pij hat. And now what you can do is, once you figure out the transition probabilities, you figure out the confidence interval as well. But again, you still are not sure that the model that I'm trying to fit to the observations that I have, is it really Markov? Does the Markov property hold true? So there is a test that you can do. But again, to check the whole distribution and to verify it fully, it's going to be much tedious. So they have defined a triplets test, which will allow you to do the same thing in a very shortcut manner. So what we are going to do now is, this is something like the chi-square test, right? Where this is the observed. So I know that Nijk is the number of times I observe a transition from I to J to K in 2 steps. And then this is the number of times I expect this transition. So what is my Nij? My Nij is again the number of times I have come from I to J. And this Pjk is the number of times I expect myself. Sorry, this is the probability that you will expect yourself to go from J to K. So that is how you define your expected number of times that you will go from I to J to K. Okay, and then you have this Nij times P hat Jk, which is the same expected in the denominator. As I have already explained, why do we have expected in the denominator here? And you square this term. And again, now you are summing it up across for all I, J, and K, because you want to take into consideration all the possibilities of I, all the possibilities of J, and all the possibilities of K. So again, I think this is not much clear here what's happening. So let us try to have a look at this example directly, I would say. So we'll state the null and alternative hypothesis. So again, whenever I'm doing a triplets test, I assume that my process is Markov. So this is the general truth that prevails. But again, I'm doubtful that whether my process has the Markov property or not. So I'm testing to see whether it has the Markov or not. So my null hypothesis is going to be that the process has the Markov property, and my alternative hypothesis is that the process does not have a Markov property. And again, under null hypothesis, you assume that Nijk follows binomial distribution with Nij as the n, and Pjk as the probability that you observe a transition from J to K. And then you conduct this test. So this is the exact same formula. And again, here you see summation Ijk. This is equivalent to writing 3 summations with Ijk respectively. So again, I know that if I have my N, I, J, K, I know that I have 3 different state space, right? And I have 3 different, so I have my I can have my J, and I can have my K. So this is something like, permutation, combination kind of thing. So what you are doing is you're trying to see how many number of possibilities there exist. So again, the number of I's that you can have is, again, it can be 1, 2, or 3. So 3 times 3 times 3. And this gives you 27. So there exist 27 combinations that you can ever have for I, J, and K. So what you will do is, you will just list down all of those combinations here. So this first column, if you see, is for I, J, K, right? And again, the easiest method to do this, I would just, tell you guys what happens generally is. So you see, we have in total 27. I know I have in total 27. So if you try to write it in ad hoc manner, it might be difficult for you to see which number you have missed out on. So what you do is you divide 27 by 3. What you get is 9, right? So you write 9 times 1. So 3 was the number of states you have. So you divide 27 by the number of states you have, which gives you 9. So you write 9 times 1 here, and then you write 9 times 2, and then you write 9 times 3. That will give you the number of I's and the number of J's and the number of K's. Sorry, that will give you the number of 1's as I's, the number of 2's as I's, and the number of 3's as I's. And then what you do is, you have, let me just maybe circle here. So you have 9 numbers where you have 1 in the first place. So now what you do is, you divide this 9 again by the number of state spaces that you have, and that will give you 3. So for 3 consecutive times, you write 1, 1, 1, 2, 2, 2, 3, 3, 3. And then again you write 1, 2, 3, 1, 2, 3, 1, 2, 3. Because that will be like, just 3 upon 3. So this is just a shortcut. I mean, you did not go this way. If you think this is tedious, you can resort to, you doing it in any way. And now you will see how many times you are observing this particular number. So 1, 1, 1. So you don't even have to go back, to the actual process. You have already taken that into consideration. So this one here will give you, so this right here is my N11. This right here is my N1, row 1, column 2. This right here is my N1 is given. So row 1, column 3. This is what? This is N1, 2, 1. This is N1, 2, 2. This is N1, 2, 3, and so on and so forth. So you do not necessarily have to calculate those Nijs and look for those again. You can directly copy down those numbers here. So 0, 1, 0, 0, 1, 1, 0, 1, 2. This is the first row, this is the second row, and this will be the third row of N1JK matrix. And that same will be true for the rest of these guys. Okay, so if you look at the triplets test, you need Nijk that you have now. And remember, before we figured out nijk, we wrote all the possible combinations of ijk. And this is actually a very important step. Okay. So next up, what you're going to do is you will have nij here. And again, you have the matrix of nij. So you can write that. So remember, when I'm writing ij here, I'm taking into consideration 1, 1 here, 1, 1 here, 1, 1 here, and 1, 2 here, 1, 2 here, 1, 2 here. So you see the number that I'm taking into consideration is 1, 1, not 1, 1 and 1, 2 and 1, 3. It is 1, 1, 1, 1, 1, 1, right? Because ijk, the place matters. Ij are the first two numbers that you observe here. So the corresponding nij for this and ijk is going to be the same for these, and so on and so forth. So you figure that out, and then again you can figure from this nij, not actually from this nij. So now to figure out this p hat jk, you will be taking into consideration these values. Probability that you go from 1 to 1, probability that you go from 1 to 2. So this was only, 1 by 6, this was I guess 3 by 6, this was I guess 2 by 6, right? And just to maybe mark it again, this was about ij, so you care about these numbers, okay? And that is how you get these numbers. So I guess, and then what you do is, to calculate your expected frequency, you will just multiply this with this, and you get your expected frequency. And once you have this, and once you have this, you can easily figure out this number for each of these 27 cases, and you sum it up across and you get your test statistic. So again, this is just something very tedious, and it's unlikely to come up in the exam because it's like just Gadamazuri. And again, I mean, they cannot even give you, they cannot even tell you to figure out degrees of freedom to compare this test statistic with the p-value or with the critical value. So because the way you know the number of degrees of freedom is a bit complicated. So either it will be given to you that this is the number of degrees of freedom and these are the values. So then you can, easily figure what's going to happen next. So I guess that was it about the triplets test, which will allow you to figure out whether the process that you're looking at has a Markov property or not. And again, here there is just one line which is very interesting, is when you're calculating the expected frequencies, Nij is calculated as Nij k, where you're summing up across all the k. So you want your Nij to be equal to these Nij k's to ensure that, the number of observed frequencies is equal to the number of expected frequencies tally. So if you remember, the only issue that you will have is about these two particular values, right? Because the number of transitions that you will have for 2 will not be the same as the number of 1 transitions that you will have. So you want to keep that equal as well. And that is why what happens in this case here, if you see, whenever you are looking at N33, so the number of 3 to 3 observations we had was 6, right? It was 6. But did we use that? If you have a look at here, it's not quite evident here, but the denominator that they have taken is actually 5, not 6. Because you know that you can observe 3, 3, but there is no way you can observe 3, 3 and then something else. So to keep the number of observed and the number of expected equal, you say that, you check the highest step that you're taking and you cut those numbers out. So at the end, what you will have to take, what you will be using is, so wait, maybe I can show that to you guys here itself. The change will be in Nij, right? So if you check Nij for 3, 3, what is it? Let me just go back. Yeah, here you have an Ij, right? So again, it doesn't matter if you have Ij here or Jk here. What matters is this taking a value of 1, 2, 2, 3. So irrespective of Ijk, Ijk's are just placeholders. So it doesn't matter which one of these you're looking at, you will still have the same. So if you look at the transition from 3 to 3, it has 2, right? So there have been 2 number of transitions from 3 to 3. But again, if you have a look here, there is no way you can go from I to J and then J to K here. So you kind of ignore that and you assume that this is just 1. So you subtract 1 from here. So you will write just 1 here. And now if you have a look, instead of 1, instead of 2, you have 1 ones here, right? For 3 to 3. So yeah, I was looking at NIJs and this is the NIJs where I see 3, 3, 3, 3, 3. So instead of 2, this is just 1, 1, 1. So yeah, you will have to keep this into mind as well. And yeah, I think this is just a bit about simulation. So here they're talking about, how you will actually simulate a Markov chain. So let us say you observe a 2-state Markov chain with this transition matrix. So what's going to happen is you expect 60% of times to be in state 0 and you expect 40% of time to be in state 1, given that you have started at 0. So what you do is, if you want to generate some random chain, if you just want to generate some random numbers, which will give you this particular transition matrix of zeros and ones, what you can do is you can just give computer a command that generate a random number u from uniform 0, 1. So whenever I'm talking about a uniform 0, 1, I know that the probability that I will observe something below 0.6 has a chance of 60%. And the probability that I'll observe something above 0.6 has a chance of 1 minus 0.6, which is 0.4. So that is 40%. So it kind of goes well with what I have here. So that is how you determine for the conditional distribution of x1, which is for the row 1, given that x0 is 0. And the conditional distribution for x1, given that x0 is 1, will be 0.3. And again, here you will have u greater than 0.3. So I guess that was it that they were trying to say here. And that's it, I guess. Yeah, so here I guess they are just saying that, again, if you have infinite state space, you will have simple transition structure, whereas your increments y, they will be, Markov. But again, sometimes, let us say if I'm defining that the chance that I will go from x to x plus 1 is theta x. So here I'm saying that this probability depend on x. It is not some constant like a half and half that we saw before. It is something, let's say half x, and let's say it is 1 minus a half x. So then I know that this probabilities vary with respect to the state I'm looking at. So again, this would be this. So in this case, the transitions, the increments will not be independent. So that is just what they're trying to say here. And I guess that sums up the chapter. Any doubts so far? Anyone? Actually, what I would suggest is, you can just revise all of the chapter again this weekend and try to solve sums from the back of the chapter as well. And you'll encounter some difficulties at start to even, figure out the periodicity, let's say, or to even graph the diagram. And if you need any help, just, message me and I'll come to your rescue. So that's no worry. But again, I think you guys, the more you practice these sums, the more efficient you will be the next time you encounter a sum, because you would have, known what all can be possible. So yeah, I guess that's all from my side for today. And I'm sorry I hurried up a bit because I have a conference which has already started. It was supposed to start at 7:30. So I think I'm just gonna wind up the class here. And yeah, do you guys have any doubts though?
No, ma'am. Thank you.
No, ma'am.
No?
Thank you, ma'am.
Okay, then. It is good having you all, and I guess enjoy the weekend. The rest of the weekend, I would say. Okay, so I'll update when will be our next class. Okay? So yeah, enjoy. I'm leaving.